impaired that overall works better in loud environments. Um, Not many visual-based devices exist for this purpose, and using lip reading allows the device to work in an environment with any amount of background noise. And the project is aimed to benefit the hearing impaired. Our team consists of myself as team leader and hardware lead, Manuel Luzencourt on our hardware team, Krish Patel as our software lead, and Nicholas Portanova on our software team. So motivation behind our project is a conversational aid that works in high background noise environments. Current systems such as hearing aids can cause difficulty distinguishing between background noise and the people in a conversation. But a visual-based system would not be affected by any amount of auditory background noise. So the proposed system will accomplish this by using lip reading to record what's being said in a conversation. Other companies that are similar to us include companies like Demand AS, who are global market leaders for development and manufacturing of products and equipments to help people with hearing loss. MedL, who are global innovators in hearing loss solutions directed towards implants and audio processors, as well as Nuance Communications Incorporated, who are pioneers and global leaders in conversational AI for a variety of industrial applications. So in summary, our project will be implemented as a handheld device utilizing a camera and a portable power supply. The device will work through Raspberry Pi 4, which will be utilizing existing algorithm to detect the movement of lips and translate them into text format. The device will be controlled over Bluetooth through an app on the user's mobile device, where the text will also be outputted to. Some societal impacts include it will help the hearing impaired have more fluid conversations, regardless of the environment that they're currently in. As well as ensuring usability helps the project to be available to a wider variety of people with hearing impairments, allowing for more people to benefit from the project. And so an overall view of our project can be seen here in these three pictures. On the left, we have our charging station. In the middle, we have our overall system. And on the right, we have our app, which is running on our Android device. So an overall system description, our project is creating a visual transcription system that's capable of distinguishing movements of one's lips and translate them into text format. We accomplished connecting a camera to the Raspberry Pi and configuring the Pi to run the chosen lip reading algorithm. We've also designed and tested a portable power supply as well as a charging system, which provides the user with multiple options for recharging the device directly. Lastly, we have designed our own mobile app, which allows the user to interface with the system as well as it logs the transcriptions.
So to go through some of the software-related theory, first we have the lip reading algorithm, which is a recreation of a published project called LipNet. It performs lip reading by mapping sequences of video frames into text without the need of breaking down the video into separate words. It performs computer vision tasks such as object recognition and feature extraction. And the training is designed with an end-to-end learning model that focuses on character level recognition rather than word recognition. And then below we can see a graph of our accuracy tests in which a speaker from the training database yields about a 92% accuracy with 75% on Robert and 82% on me. And we consider this passable based on our engineering requirements.
All right, so hardware-related theory. So overall, our project hardware consists of two main circuits along with the Raspberry Pi. Those are the power supply circuit and the charging circuit. The power supply circuit functions through the use of a 3.7 volt lithium-ion battery that is connected in series with the boost converter circuit. The boost converter steps up the voltage from 3.7 to the 5 to 5.5 volts needed by the Pi. Additionally, there's a switch used to open the connection between the output of the boost converter and the input of the Raspberry Pi, allowing the user to turn the system on and off at will. The charging circuit utilizes a specialized microchip designed for charging lithium-ion batteries and also features filtering capacitors, current limiting resistors, and LED indicators in the circuit. An additional switch was implemented to enable the user to charge the system via solar panel or wall outlet. There are various USB receptacles that serve as input and outputs to the system circuits. We also had a custom PCB and 3D prints that were designed and created for the overall hardware. And lastly, the battery itself will run for about 104 hours with the system and takes about 24 hours to charge. All right, so this is our hardware implementation. These two images represent the general schematics used in designing the two circuits. On the left side, you can see the schematic depiction of the power supply circuit. As mentioned in the last slide, the lithium-ion battery feeds into a boost converter circuit that steps up the voltage, which then outputs it to the Pi. You can see where the charging circuit also feeds into the power supply when it gets connected to the system. And on the right-hand side, you can see the schematic view of the charging circuit. The charging circuit mostly features the special microchip that has 5 pins that regulate the circuit. There are 2 resistors, one for the LED, which stays on while the battery is charging, and the other one which sets the charge rate. And you can also see the 2 filtering capacitors and the USB receptacle. All right, so iterations. All right, so here you can see the actual power supply circuit that was made. On the left side, the left side shows the circuit when it was originally set up for testing, while the right side shows the actual configuration of the power supply housed inside the handle of the unit. The handle features cutouts and openings that allow for all ports, cables, switches, and LEDs to be seen and accessible with the handle closed up. And here we have the iteration of the charging circuit that we used for the product. On the left side is an earlier iteration of the charging circuit that just features charge by solar panel. And on the right is the final iteration being demonstrated today with both the solar panel and wall outlet both functioning. The lid is currently flipped upside down, so you can't see the solar panels. And originally, this circuit was set up to be housed on a custom PCB that we designed, but unfortunately, the PCBs were malfunctioning and we couldn't have that ready in time for the final demo.
So here we have a few pictures to show the software implementation on the Pi side of things. First, on the left, we have the Python script that handles the automation of the whole process of creating the Bluetooth connection, recording the video, passing that as an input along with the weight file. Then we have the predict function that formats all these parameters and allows to start the processing. Then the picture here is one of the outputs that we could see the transcribed text on the video, and then the picture of the terminal just shows the text output itself. And here on the app side of things, we have the first on the left that shows the shared preferences, setting up the key value pairs to save the user credentials. In the center, we have the database setup using SQLite. Then on the right, we have the function that handles the setting up the connection from the Pi and the phone. And to go through some of the iterations here, the first design, as you see, we have an option to change the duration to record for. In a later iteration, we took that out just to streamline the whole process and to meet our requirements. And then the final one just shows the login screen that was added on top of everything else just for verification.
So here are some examples of the unit tests we did for the project. So on the left, we have the final power supply circuit test, which succeeded in outputting the 5.5 volts that were required. And on the right, we have the test for the algorithm output, which was successfully able to transcribe sentences using grid language, or language from the grid database. Here are integration tests. On the left, we have our overall circuit, which includes the power supply circuit successfully outputting its 5.5 volts and the charging circuit succeeding with its 3.4 volts. And then on the right, we have testing the mobile application connecting to the Pi. So the Pi was able to create a Bluetooth socket, which the phone could connect to, and then send the transcription command, which allowed the Pi to send the transcription back to the app. And then here are acceptance tests. On the left, we just have the system as a whole, which is the charging circuit connecting to the power supply to power the Pi, which can then connect through the phone to Bluetooth and then go through that system. And then on the right, we have our accuracy test. So when testing the speakers that the algorithm was trained on, we got an average accuracy of 94%. But then when we tried to do our group members just with regular lighting, the accuracy was a low 27%. So in order to compensate for that, we just improved the lighting, and then the accuracy was able to increase to about 80%. However, if you were to use just regular vocabulary and language that isn't in the grid database, you get poor results. So we'd have to retrain the algorithm with different language if we wanted to account for that. And then here's our corrective actions chart, which just shows all the tests that we did and then the corrective actions to accommodate for failures. And then for challenges in future work, for this project, we successfully designed and built a working handheld system that was capable of recording and transcribing a person's lip movement through assistance of a mobile app and charging station. For the power supply, we overcame the challenge of getting it to a sufficiently small size so that it could fit in the handle. For software, we overcame the challenge of properly setting up all the modules so that it could run on a Pi OS. And then, given more time, we would work on training the algorithm more so that it could have a larger vocabulary to work with. And we also could have finalized the PCB design and finished the errors that came from that. And then also, instead of a Raspberry Pi, we could design it for a custom board, which could be more optimized towards running the algorithm quickly. And then outside of the classroom, we had to learn PCB design using Eagle, 3D printing using AutoCAD, and Python coding, along with Bluetooth communication. Sorry, and there was our Gantt chart that just showed the timeline of the project.
All right, so here we have our overall bill of materials. About halfway through the project, we exceeded the budget limit and wound up having to pay for the rest of the materials we used out of pocket. So that gave us a total price of $483.62.
Okay, so we have our demonstration video here, which I'll play.
Hello everyone, we're Team eyeMouth and this is our physical demonstration. So our project consists of three main parts: our app, which is loaded onto our Android device, our main system, which we have our custom 3D printed handle encompassing all of our electronics with our Raspberry Pi and our camera mounted on top, and our charging circuit electronics also encased inside our custom 3D print with our solar panel mounted on top. So how our project works: user has an app that they can download onto their phone. Upon launching the app, you are brought to the login menu. If an account is not already made for the user, they can go over here and click the register button, in which they will be prompted to create their credentials. But for this purpose, we already have an account made, so we'll go ahead and log in. Upon successful login, you're brought to the home menu, and then you can start setting up the system. So the main system has a on and off button attached to the bottom of the system, allowing the user to toggle the system on and off. So we'll go ahead and start the system. Now we're going to wait for the red LED to turn on, indicating that the system is ready to connect with the phone via Bluetooth. Okay, so now we're going to go ahead over to the app and hit the connect button. Upon successful connection, the LED will turn off. So now that we are connected, we can go ahead and record a video. I have my partner Krish Patel here with me, so we're going to go ahead and record him. So I'm going to angle my device at him and go ahead and click the record button.
Place white with you too soon.
Okay. So now we're going to wait for the LED to come back on. And the LED is on, indicating that the system is now transcribing the video. While that transcribes, we can go over here to the charging circuit. So the charging circuit has a switch on which allows the user to toggle between powering the system via solar panel or wall outlet. we're going to go ahead and power this via the wall outlet for this demonstration. And then whenever the user needs to charge the system, just go ahead and plug it in. All right. And upon connection, the LED indicator would turn on. Right now the battery is fully charged, so the LED is not going to turn on. But the user also has LED indicators inside the system, a red one on your right and a green and yellow one on the left. Right now you can probably see the green LED laying on indicating the battery is fully charged, but upon low battery, the red LED would turn on. But we're going to go ahead and disconnect that since we're fully charged. Turn off the charging station, and we're going to wait for the LED to flash, indicating that we can now acquire the transcription. Okay. Upon flashing, the video transcription is ready to be acquired. So we're gonna go ahead and hit the get button, and now we see the transcription has been sent to the phone, and the user can now record another video if they wish. Yeah, so that is our system. Thank you.
Okay.
All right. So here are some of the codes, standards, and constraints associated with our project. An example of a standard that we complied to for this unit was the FCC Grant of Equipment Authorization, which allows the Raspberry Pi to be used as a standalone product for our uses. Some constraints we had were having to use Python version 3.7 to allow us to have longer term support, as the 3.7 version comes with more features and higher security. We also had to use Bluetooth 5.0 to allow for greater compatibility with more devices. And an example of a code we adhered to was the Electronic Code of Federal Regulations, which ensures the ability to bring the system onto all sorts of transportation services.
And here we have a series of statements addressing the various ethical issues concerning our project. And to go through some of the engineering complexity, we have our project applied concepts from fields of electrical and computer engineering, such as power electronics, green energy, PCB design, machine learning, Android development, and object-oriented programming. We also incorporated 3D design and printing concepts with help from a fellow mechanical engineering student. One of the major issues we faced was implementing the algorithm onto a Raspberry Pi, which required a reorganization of the several layers and updating Python 2 code to Python 3. And we also faced issues in the circuit design concerning voltage drops and solar panel capabilities. We have a list of references here. Thank you, and at this time, we'd like to open it up to questions.